Good afternoon, colleagues. We're glad to present our research on the DAM digital wireless mini sensor of plant thermoregulation. Agriculture cannot develop without the use of modern technologies. Modern multi-story vertical agricultural complexes already widespread in Japan, South Korea and Australia, and now built around the largest Russian cities such as Moscow, Petropavlovsk-Kamchatsky and Novosibirsk. In such complexes, which are in fact modern closed agro-ecosystems, the latest technologies are used to optimize the production process, to increase the amount of products manufactured per unit area, and to reduce transportation costs. Sensors and transducers are always used on intelligent farms of an intensive type. They provide initial information of change in the state of plants, including on deficiency states, as well as on environmental indicators in which they are grown. Such information makes it possible to control the technological process of agricultural production by building an algorithm to make decisions in intellectualized control systems. Timely monitoring of the plant condition is necessary to understand its physiological status and can help prevent negative effects of environmental stress and increase agricultural production. In connection with the intensification and digitalization of agricultural production, this task is relevant both for open ground and for protected ground, especially when using phase-wise regulation of the intensity and spectral composition of radiation. The main indicators characterizing the physiological state of plants and associated with their productivity include transpiration, the most important function of which is thermoregulation. To protect themselves from overheating, plants regulate their temperature by evaporation. With intensive transpiration, the leaf temperature can be several degrees below the temperature of the leaf in which transpiration doesn't occur when wilting. The operation of the operant motor is also conditioned by leaf transpiration, and it is supported not only by metabolic energy but also the energy of external environment. The plant spends approximately 1% of consumed water for photosynthesis. Approximately 5% of consumed water is spent for the transfer of nutrients to various organs. And the rest of consumed water is spent for thermoregulation. Thermoregulation in plants is of key importance in maintaining photosynthesis and its maximum temperature level. The main function of thermoregulation is to reduce the temperature of the photosynthesizing leaf, which captures the thermal energy of light radiation, and to maintain the optimum temperature of photosynthesis by lowering the leaf temperature. Since the plant is a self-organizing structure, the main processes occurring in it are subject of the law of synergetics and to the principles of extreme energetic self-organization according to the law of survival. The non-linear dynamic process of transpiration occurs due to the external energy of the environment, thermal exergy. Thermoregulation occurs due to evaporate cooling in the stomatal parts of the plant and has a limited effect due to the limits opening of the stomata themselves. In this regard, the process of thermoregulation can be represented in three phases. Phase 1. The ambient temperature is below optimal. The ambient temperature and the temperature of the plant are equal, since the plant does not have internal sources that can increase its temperature. Phase 2. The ambient temperature rises and becomes higher than optimal temperature, but the plant is able to cool itself and reduce its own temperature to optimal indicators due to the cooling evaporation of moisture from the leaf surface. The difference between the ambient temperature and the temperature of the plant has a final growing value. Phase 3. the ambient temperature is higher than the optimal temperature, but the plant is no longer able to cool itself to optimal values. That is, the temperature is so high that the plant exhausts all its cooling capacity and the plant temperature begins to rise following the ambient temperature. In industrial plantings, to determine the parameters of plant transpiration, local methods for determining the amount of evaporated moisture are used in individual areas along the entire perimeter of the site with subsequent extrapolation. The weighting method has hitherto been considered the main methods for determining the intensity of transpiration of herbaceous plants. For woody plants, the water flow rate is determined by the linear velocity of water flow and the volume of water passing through a unit of water conducting slag. These methods are rather laborious and do not allow for non-destructive monitoring of the transpiration intensity in vegetable plants directly in the place of growth. Measurement of turgor and the parameters of variable fluorescence of the leaf apparatus of plants are much more informative for monitoring the stress states of crops. The purpose of our research was to develop and to test experimentally a sensor in the course of digital assessment of thermoregulation processes and to confirm experimentally the phasing of the thermoregulation process. To access the thermoregulation process in leaves and control plant productivity by changing the control variable, we developed a leaf mini sensor. The sensor body was made of polylactide polymer, which is a biodegradable material obtained from renewable resources such as maize or sugarcane. The material is highly biocompatible. It is also used in medicine for the production of surgical sutures and pins. The body was equipped with a special pin for attaching the sensor to the plant's leaf. The force of the pin preserved the leaf surface tissues. The upper part of transducers was equipped with a spherical photoconductive dome. The dome was made of thin-walled glass, which provides sufficient light transmission to ensure the photosynthesis process inside the glass. The transducer was also light, with a wire and weighted 8 grams. The dome diameter was 18 millimeters. You can see it on figure 9. Such a design eliminated previously unresolved environmental problems such as dust, steam, etc. The developed device was equipped with 2 built-in digital sensors: air temperature sensor and infrared non-contact temperature sensor. The SI7029 I2C humidity transducer is a monolithic CMOS integrated circuit that includes temperature transducer integration, analog to digital converter, signal processor, calibration data, and I2C interface. The temperature transducers are factory calibrated. The calibration data are stored in the built-in non-volatile memory. The infrared sensor for measuring the surface temperature of the leaf runs on the MLX chip with a 70-bit digital output signal using the I2C protocol. The output signal of the transducers is digital. It is transmitted with I2C protocol, which is compatible with all modern digital controllers, data transmitters, and other Internet of Things equipment. This allows a large number of transducers to be integrated into the Internet of Things system. The leaf sensor can be connected to a processor such as Arduino, which processes input data for the chamber temperature and the surface temperature of the leaf. The data is then transmitted to the data logger with a serial port or radio transmitter. The radio transmitter operates with the LoRa protocol, which provides low-speed, long-range data transmission. The transducer was powered with a USB port from the external battery power bank with a capacity of 10 amperes per hour. Provided that the enhanced signal transmission is disabled, the consumption during data transmission is 4 milliamperes. The data obtained from the leaf sensor were used to study the issues of plant thermoregulation from the bioenergetical standpoint, taking into account phases in the process of thermoregulation. The characteristics of the processes were measured automatically several times using a recorder in the period from 13th January 21 to 29 January this year. The measured data was achieved on a SD card and then processed on the computer in the Microsoft Excel. The key component of the recorder was a PLC by an Atmega processor equipped with analog and digital inputs and outputs, a real-time clock, device for storing on a micro SD memory card for fixing data, and Wi-Fi module for transferring them to cloud storage or an internet database. From the received data, we formed lines which were separated by commas. Each line was written separately into a CSV file on the memory card and sent to the MySQL connection library. The developed leaf sensor has a number of advantages, including the use of modern digital communication protocols. The I2C data transfer protocol allows the transducer to be used with all modern Internet of Things devices, while the energy-efficient radio transmitter LoRa provides wireless connection of the transducer to the system for controlling light climatic parameters at distance up to 200 meters. The cost of the leaf sensor is approximately $13 in prices of 2029. This makes it possible to massively use sensors of this type in closed artificial chambers and vertical farms, while receiving a large data array which can be used for further analysis and development of control solutions for the automation systems. If necessary, it allows for individual control of plant parameters. However, the operation experience showed that the reliability of the transducer directly depends on the build quality of the sensor's strapping boards. When using inexpensive components, the share of reject sensors was approximately 5%. Service life of another 5% was no more than 30 days. Using the transducers on a plant for more than 7 days without changing the position led to an increase in the reading error due to possible damage of the leaf or adaptation of plant cells to a foreign body. In particular, this led to disruption of the stomatal apparatus and consequently thermoregulatory properties of the leaf. Data were registered with a 5-minute interval. For each measured parameter, we recorded of total 4,896 values. Due to the fact that it is difficult to show such an amount of data within the framework of the article, the obtained data were presented in the form of graphs of time series of measured temperatures. The graph distinguishes an area with a constant temperature of 29.2 degrees. The difference between the values didn't exceed 1%, which is acceptable. Thus, there are three phases of thermoregulation. So in phase 1, an increase in plant leaf temperature was observed following an increase in air temperature. In phase 2, the plant leaf temperature stabilized at the air temperature of 29.3 degrees. In phase 3, the plant leaf temperature continued to grow after an increase in air temperature, while maintaining a constant maximum temperature difference. Experimental studies revealed the three phases of plant thermoregulation. Further research should be aimed at theoretical and experimental confirmations of the hypothesis that the maximum productivity of the plants is provided at the optimum air temperature and maximum consumption of nutrient solutions. If this hypothesis is confirmed, it is necessary to develop an universal algorithm for controlling the air temperature in closed agroecosystems, which ensures the search of the temperature at the boundary of phase 2 and 3. This algorithm corrects the ambient temperature and controls the temperature difference between the leaf and the air and the ambient air, determining the maximum difference at the lowest possible air temperature that provides a rational maximum consumption of the nutrient solution by the plants. So, summing up the results of our research, we can draw the following conclusions. As part of the recorded, the digital mini sensor of plant thermoregulation showed satisfactory functioning. Its indicators corresponded to the indicators of the sensors used in it. We studied the process of plant thermoregulation with an increase in air temperature and experimentally confirmed the presence of three phases. We noted that the phase 2 corresponds to the constant leaf temperature, that is, to the temperature optimal equal to 29.3 degrees for tomato. Confirmation of the presence of thermoregulation phases allows developing an intelligent algorithm for controlling the climatic parameters of plant growth to ensure maximum productivity and economical use of resources. The digital mini sensor for thermoregulation of plants as part of the system for managing growing conditions can be used to control and maintain optimal productivity of plants in open and protected grounds, which is especially important under changing light conditions. Thank you for your attention.